Hi class, we are now on 16.6. This is a reaction quotient predicting the direction of change. So equilibrium constant represents a ratio of concentrations or partial pressures of the products to reactants at equilibrium. So we can determine by looking at Kc, if it's a large value of equilibrium constant, then we know that equilibrium has shifted towards the right, towards more product. Basically, if it's above 1, and how large that number is really tells us how much. If we have a small equilibrium constant value, which is less than 1, then it's shifted towards the left, meaning it's going to have more reactant than products. When the system is not at equilibrium, we can't do this. This only works at equilibrium with the concentrations at equilibrium. However, we can use what is called the reaction quotient to determine using the same, and we use the same ratio as equilibrium, so nothing's going to change but the letter of QC from Kc. But we can use concentration or partial pressures when the system's not at equilibrium. And this is a good thing to if you're trying to keep an eye on a reaction, you can use QC to see if the reaction is really at equilibrium. And if it's not, it helps you give you an idea of where it's at. And this is helpful when the reaction is really, really slow getting to equilibrium or to the products. So the reaction quotient is a reaction mixture containing reactants and products, and it specifically is not at equilibrium, but we can determine which direction the reaction will reach at equilibrium. So we can see which direction the reaction's going in, pretty much. The answer is to compare the current concentration ratios to the equilibrium constant. So what we're going to do is use the same stuff. We're going to plug everything into the reaction quotient, which is still the equilibrium quotient, the same thing, but we would use QC instead of Kc. Then we can take that value and we can compare that value to the equilibrium constant value, and that will give us an idea of where the reaction is. So the non-equilibrium concentration ratio of the products raised to the power, so we're still raising the power of the coefficients to the reactants, and we're raising the power of the coefficients to the products, and that's what's going to be the reaction quotient. So here is the reaction quotient. It looks the same. Like I said, we're simply replacing the Kc with QC, or the Kp with Qp. So we can either do this for concentration or partial pressures. Everything will be exactly the same. So if a reaction mixture containing both is not at equilibrium, again we can, I think I went backwards. There we go. So we can predict the direction in which the reaction will shift by comparing the values at the end. So when Q equals K, that means the reaction is at equilibrium and no shift is occurring. There's no change happening still. When Q is greater than K, then that means that more reactants must be formed to achieve the equilibrium, and the reactions shift left. So what that means is that the concentration, so when Q is greater than K, the concentration of the products is too large and that of the reactants is too small. So it's got to try to balance itself out. The reaction achieves equilibrium by forming more reactants, so it proceeds from right to left. So it's trying to adjust itself to get to the equilibrium constant. So if too much was made, because we know what the equilibrium constant value is, so if this value is too much above it, it's trying to shift itself and get it back down closer to the equilibrium constant. Now, if the Q is less than K, then that means more products must be formed to achieve the equilibrium, and the reaction shifts towards the right. So this means that the concentration of products is too small and that the reactants is too large. So it hasn't gotten close to equilibrium constant yet. So the reaction achieves equilibrium by forming more products, and it proceeds from left to right. And this is exactly what I said. It's, in a sense, okay, so we have equilibrium where the Q is lower than the K. So if Q is less than K, it's got to make more, so Q is less than, the concentration of products is too small and that of the reactants is too large. So the reaction achieves equilibrium by forming more products. It proceeds from left to right. I don't know if I said that right. Hold on, let me look at my notes. Okay, yes. So basically, we're trying to get this up to here. So in order to do that, it hasn't reached the value. The Q value is smaller than K. So it needs more products in order to get to this line. Now, when there are 1 and 1, that means that the Q is at equilibrium with K and nothing needs to happen. And when we look at this one, now these are the products. So what we're looking at is products. And this Q has too many products. So it overshot the equilibrium constant. So it needs So the concentration of products is too large and that of reactants is too small. So it's going to push itself back down. So it's going to have the reaction go towards the reactants. So it's going to go to the left so that it can remove this excess of too much products and get this back down. Okay, so the reaction quotient is relative to the equilibrium constant. It's a measure of the progress of a reaction. So this gives us a good idea of where the reaction is based on the equilibrium constant. But we must have the equilibrium constant in order to compare it, or it doesn't work. Okay, so here we can look at, so calculate QC for this reaction when the reaction mixture contains 0.32 molar of bromide, 0.37 molar of chloride, and 0.15 molar of bromium chloride. So we have everything. We have the concentrations. We just got to plug this in, because the main thing that we're going to do here is we're going to plug it in to get the quotient reaction quotient value. And once we get that, then we can compare it to the equilibrium constant, and that will tell us where this reaction is. So if we look at this, we plug everything in, nothing changes, we raise the coefficient to the power, and this ends up giving us a 5.3. So we have this value as 5.3. So now we're going to plug it in and compare it to the equilibrium constant. And you can see that this is far smaller than the equilibrium constant. So this reaction has a long way to go still. It hasn't quite gotten up to equilibrium. So it's going to go towards the products. This reaction is still going towards the products to lift this value up to get it close to the 377. All right, did I pass this? Okay, so for the reaction, we have a reaction here, and a reaction mixture at a certain temperature initially contains both the reactant and product in their standard states. So we're looking at, so the partial pressure of N2O4 equals 1 atm, and the partial pressure of NO2 equals 1 atm. If the equilibrium constant at partial pressure is 0.15, which statement is true of the reaction mixture before any reaction occurs? So basically, how do you do this? Well, you set it up with the quotient. I keep forgetting how to. You set this up with the reaction quotient, with what we have for the partial pressures. So we set it up with the reaction quotient. It gives us 1. Now we have values to compare. That's basically what you're trying to do. You're trying to get to the reaction quotient so that you can compare that with the equilibrium constant. So this is showing that Q is greater than the the equilibrium constant for the partial pressure. So Q is greater than K. This reaction is going to go left because it's way above what the equilibrium constant is. So this would be C. Okay, so let's do a review. Unlike the equilibrium constant, the reaction quotient describes the ratio of products to reactants at any time during the reaction. So this is good because it's good to understand mainly what the difference is between the equilibrium constant and QC. So with equilibrium constant, you only have one value. That value doesn't change. Remember I showed you that table in the last section that the KC is all the same even when the initial reactants different concentration. So the KC is one value, and it specifies the amounts of reactant and products at equilibrium. So it has those amounts at equilibrium. The reaction quotient depends on the current state of the reaction and has many different values as the reaction proceeds. So that's a big difference here. We have one that must be at equilibrium, and we have one that we can check throughout the reaction. So this is, so we can check it anytime during reaction is what it means, and we'll have many values for it. The reaction quotient is used to predict how the concentrations or partial pressures of the products and reactants must change to reach equilibrium. If the equilibrium is equal to the reaction quotient, the reaction is at equilibrium. If Q is greater than K, then the reaction will need to shift back to the left because it made too much product and it needs to get back down to try to match the value of equilibrium constant. And if Q is smaller than K, then the reaction hasn't gone far enough and it's got to keep going towards the right to achieve equilibrium.